I am Dr. Pavitra Bharadwaj. I am Associate Professor in the Department of Computer Science, Jesus and Mary College at the University of Delhi. So friends, we have been talking about various issues related to the operating system, and in the last two lectures we were talking about a very interesting topic on CPU scheduling. So if you will recall quickly, we will take a very quick recap at what we had discussed broadly in the last lecture. So we had seen that in order to facilitate multi-programming or multi-processing, computers, they need to organize the processes in a way so that the CPU is utilized at the maximum. That is, the ideal computer is a computer which has got the maximum utilization of its CPU. That is, the CPU should remain idle for the minimum amount of time. Now, how is that possible? So, that is possible by aligning or by arranging the processes in a way so that the distribution of the two phases of a process, that is the IO burst and the CPU burst, that is when the process any process is requiring the input output or when the process is requiring the CPU. So, it should be divided in such a way that the CPU remains busy at all the time. So, when one process goes for its input output IO burst, that is called, the other process can take over the CPU, and in the meantime the process can come back and wait in the ready queue. So, this was broadly what scheduling means, right. Now, how this is done? So, there are multiple ways in which these schedulings can be done, and there are multiple algorithms which suggest different ways of scheduling or different ways of organizing these. So, there is a module in the operating system which is known as the scheduler, or which is whose function, which is actually the short term scheduler, whose function is to organize the processes, to schedule the processes in order to maximize the utilization of the CPU. And then we have the dispatcher module. The dispatcher module's job is to lodge and dislodge the processes or to assign the processes to the CPU. So, basically when we are talking about scheduling, so scheduling algorithms are a very important aspect of this, because using these algorithms or using these frameworks, operating systems are designed so that they will follow the best possible way in which a process can be scheduled or different processes can be scheduled. So, these scheduling algorithms, they are nothing but they will suggest the various ways in which the average waiting time of a process is minimized. Well, what is waiting time? We had discussed. Waiting time means that the time for which the process is there in the ready queue. Ready queue means that the process is ready, but it is waiting for its turn to get the CPU. So, the ideal algorithm will be which will allow us the minimum waiting time, which will allow a process the minimum waiting time, right. So, if it is only a single processor system, definitely then there is no problem, because then it is only a one process which can run the CPU at all the times. But of course, this is not the case that we are discussing. So, because of multi-programming environments, CPU scheduling is inevitable. So, in the last lecture we had discussed about two main algorithms, the first in first out algorithm and the shortest job first algorithm. So, first in first out algorithm was a simple queue algorithm in which the processes, they enter from the tail end and they are assigned from the head end. So, this works in a simple format like a normal queue works. A normal queue at a bus stop maybe will work. So, in this case, this is a non-preemptive algorithm. Non-preemption and preemption also is important to understand. Preemption means that if a process is executing in the CPU, it is still running in the CPU, another process is able to preempt and take control of the CPU and put this process out, right. So, first in first out is a non-preemptive algorithm, that is, once the CPU is assigned to a process, it cannot be taken back unless the process itself finishes or it goes for an IO. Other than that, the process will have control of the CPU. And we had also seen that the first in first out algorithm, it is not the best algorithm. In fact, it is a very simple algorithm, but there is a average waiting time is quite more in the first in first out algorithm. Also the sequence in which processes come will also make a difference in the first in first out algorithm. So first in first out is the most simple, but it is an inefficient algorithm for CPU scheduling. Then we had discussed about the shortest job first algorithm, in which the jobs are assigned in according to the time they need for the CPU burst. That is, the CPU burst, with the process which has got the shortest CPU burst will be given the charge of the CPU first, and those which need the CPU for a longer time will be asked to wait more. So shortest job first algorithm can be preemptive as well as non-preemptive. So again, preemptive means that if a job comes which requires the CPU for a lesser amount of time than what is left for the ongoing or executing process, then the process will be preemptive. So sometimes this is also called as the shortest job next first algorithm. So actually in this, the time which is calculated on the basis of the next CPU burst. And we had also seen that what are the challenges we face in order to calculate the next CPU burst for that particular process. Now today we are going to talk about a third type of algorithm which is also very interesting and important, that is the priority scheduling. Now priority scheduling is also, actually if you look at the shortest job first algorithm, shortest job next algorithm also, these are also priority algorithm, because in this also the priority is associated with the process, right. But if you talk about priority scheduling in general terms, so it is associated with each process, and CPU will be allocated to the process which has got the highest priority. In our day-to-day life also, when a resource is scarce, then how do? We actually prioritize the utility of the resource. So same here also we are doing, because CPU is a very dear resource for the system. So therefore we are going to prioritize, and the process which has got the highest priority will be given the CPU. If two processes come who have the equal priority, who have same priority, then they will be scheduled in the first come first serve, that is the FCFS order. So they will be dealt with in the simple queue format. So the shortest job first algorithm is also, as I just said, it is also a priority algorithm. And what is the basis of setting the priority there? The basis of setting the priority is the inverse of the next CPU burst. Inverse of the next CPU burst means that the larger the CPU burst, the lower will be the priority. This is what SJF does. The process which has got the highest amount of time with the CPU, which needs the highest amount of time with the CPU, will be given a lowest priority. So here also in the priority scheduling, we can use different numbers basically to indicate the priority. So this range could be fixed. So somewhere we see that the range is between 0 to 7. At other places we see that the range of priority is 0 to 4095, 4095. But there is no general agreement as in which is the highest or lowest priority. That is, when I say 0 to 7, so 0 means the highest priority or 7 means the highest priority. So therefore some systems, they use lower numbers to represent lower priority, others will use lower numbers for higher priority. So therefore this can be a little misleading, this can be a little confusing, right. But actually most texts, they will show that lower numbers will represent a higher priority, that is they will show the precedence. So for example, if we have 3 processes, one has a priority of 0, the other has a priority of 7 and the third has a priority of 2. So the process which has 0 priority is higher priority than the other 2 processes. So lower the number of the priority, higher is the priority which is given to the process. So if we look at this example in which we have got 5 processes, and we assume that these processes, they all come at the same time, they all come at time 0, and the order in which they come is P2, P1, 2, 3, 4 and 5, and the length of the CPU burst, that is how much time the CPU they require the CPU for, is also given here. Like process P1 requires 10 milliseconds, process P2 requires 1, P3 requires 2, P4 requires 1 and P5 requires 5 milliseconds, and then the priorities are assigned. So, as we just saw that priority is a number which is associated with the process. So, here we see that the highest priority process is the process P2 because it has got the priority 1, that is the first priority, and process P4 is the lowest priority because it has got the priority value of 5. So, therefore, in this, how the processes will be arranged, the processes will be executed in this order. So, first it will be P2 because it has got the priority 1, then it will be P5 followed by P1, P3 and P4. So, this way if we calculate the average waiting time for these processes, so the average waiting time is coming out to be 8.2 milliseconds. So, how do you calculate the average waiting time? So, we will add 0 because 0 is the waiting time for P2, 1 is the waiting time for P5, then 6 is the waiting time for P1, 16 is the waiting time for P3 and 18 is the waiting time for P4. So, we will add these and finally, we will divide them by 5 like we have done in the previous examples, and therefore, we get the average waiting time of 8.2 milliseconds. So, we see that this is quite a large value for waiting time. A process should aim at finishing earlier than this. Now, priorities, they can be defined both ways. There can be internal priorities or they can be external priorities. So, internal priorities basically they use measurable quantities to compute the priority of a process. For example, the time limit or what is the memory requirement or the number of open files or the ratio of IO burst to average CPU burst. So, these are used for computing priorities for internal basis, internal priorities. If we look at external priorities, so those are set by the processes or the criteria which are outside the operating system. Now, what are the outside operating system? So, it could be the importance of the process, the type and amounts of funds being paid for the computer use. So, if the department which is sponsoring the work is involved in the process belongs to that department, then the priority of the process will change. There can also be some external undefined factors like political factors within the organization which are also going to determine that which processes will gain a higher priority over which processes which are having a lower priority. So, external and internal priorities can be set. Of course, internal priorities are all controlled by the operating system. External priorities are controlled by factors which are over and above the control of the operating system. Now, priority scheduling, we have seen that because a number is assigned against the priority for each process. So, this could be preemptive scheduling or this could be non-preemptive. So, priority scheduling can be either preemptive, that is when a process will arrive at the ready queue whose priority is higher with compared to the process which is currently running. So, then this process will be preempted, that is the CPU will be taken from the low priority process and will be given to a high priority process. So, basically the CPU can be preempted by a process whose priority is lower than the priority of the currently running process. In non-preemptive priority scheduling, it simply that the new process which is coming will be put at the head of the ready queue. There is the process cannot be preempted. Once the CPU has been assigned, then no process can take the charge or take the control of the CPU. Now, what is the major problem with priority scheduling? Now, the major problem which we will see here is infinite blocking or what we commonly called as starvation. Now, starvation means that a process which is ready to run but it is waiting for the CPU is considered to be blocked, because a process wants the CPU but it is not getting the CPU. Now this is happening because the priority of this process is very low. So the low priority process is going to wait indefinitely, because every time the process wants to load, a higher priority process comes and it takes the CPU. Now if we are considering the example of a heavily loaded computer system, where we have a steady stream of high priority processes, then this can prevent a low priority process from getting the CPU ever. So the process will go on waiting. So now what will happen? Two things can happen in this case. First thing which can happen is that either the process will eventually run, or the computer system will crash and lose all the unfinished low priority processes. So it is said that once a computer in 1970s was shut down, and they were found processes which were started almost 2 to 3 years back, which were still lying, which were still waiting for getting the chance of the execution. Why? Because of this scheme, because they were low priority processes and they could not get to execute even till 3 years of the running time of the system. So now what is the solution to this? How can we prevent a process from getting starved or from indefinite waiting? The solution to this is that we provide the phenomena of aging, right? So a low priority process cannot wait indefinitely, right? So this indefinite blockage has to be solved, and how it is done? It is done using aging. So whenever a process is waiting for the system is waiting for the CPU control, then automatically the priority of the process will have to be reduced each time, right? For example, if we have a process whose priority is 127, right? Now this is the highest priority in the system, right? So therefore this process will have to wait. Now what will happen? Each time an execution occurs, the priority of this process will be reduced, it will be actually increased. So the number will go on reducing from 127 to up to 0, right? So it will, in around say 32 hours, a process with priority 127 will age and it will become a priority 0 process in 32 hours. This is a study which has been done. So therefore aging will actually involve gradually increasing the priority of the process which are waiting for a long time. So therefore every time an execution occurs, the age of the process will increase, that is the priority of the process in the execution cycle will increase, and therefore there will be no process which will have to wait indefinitely or which will have to be blocked indefinitely. All processes are going to get a chance, maybe a little later in a few hours, but they will all be executed. So this is a very important type of scheduling algorithm that we have seen, that how processes can be scheduled based on their priority. Now the next type of scheduling algorithm that we see is very interesting algorithm, which is known as the round robin scheduling algorithm. Round robin scheduling algorithm. So this word round comes here because in this the ready queue is actually treated as a circular queue, right? So if data structures have been done, then the students would understand what is the difference between a simple queue and a circular queue, right? So in round robin schedule, this is basically round robin scheduling is very, very useful in case of time sharing systems or real time systems, where every process has to get a slice of the CPU's time, which we call as the time quantum or the time slice. So this is a small unit of time and it is called the time slice. Generally in the modern day systems, this time slice could be 10 to 100 millisecond. So actually the queue is implemented using the FCFS scheduling, that is first come first serve scheduling, but preemption has been added to it, so that the system can switch between the processes. In our FCFS we had seen that that's a non-preemptive algorithm, that is the process which has got the CPU cannot be preempted, but in round robin we are using a circular queue, and in this the process can also be preemptive. So this is very interesting, because in this we will be talking about another dimension or another attribute of the the entire scheduling process, that is called the time slice or the time quantum. Now the CPU scheduler basically it goes round the ready queue and it allocates the CPU to each process for a time interval of up to one time quantum. Now it is important to understand that this one time quantum could be any figure, it could be 10 milliseconds or it could be 20 milliseconds or it could be even 100 milliseconds, but each process will get the CPU only for one quantum time at a given instance. So first the ready queue is treated as a FIFO queue of the processes, and new processes are added to the tail of the ready queue. Now the CPU scheduler picks the first process from the ready queue and it sets a timer to interrupt after one time quantum and dispatches the process. So first the CPU is assigned to the process which is coming in the FCFS queue only, but another parameter is added, that is a timer is set to one time quantum. Say for example the timer is for 10 milliseconds. So if a process has started and it requires 10 milliseconds, it is okay, but if the process requires more than the time quantum, then the process can be preempted. So when a process has been dispatched, then the CPU can have a CPU. Now the process which is working, there can be multiple attributes to this, or there can be multiple possibilities of what will happen. So the first possibility is that the process can have a CPU burst of less than one time quantum. So in this case the process will release the CPU voluntarily as soon as it finishes. The scheduler will then proceed to the next process. What are the other possibilities which can happen in this case? That we will be discussing in the continuing lecture. So till then please keep watching CEC. Thank you.